All right, welcome to this Masterclass Review Explainer. Look, we're setting t equals 0 today. Forget the past, we are starting completely fresh. If you feel like you've fallen behind, seriously, just leave it behind you, because today we're going to build exactly what you need to absolutely ace your Class 12 electrostatics exams. We're zeroing in purely on the core definitions, those vital formulas, and the exact problem-solving frameworks you're actually going to need on test day.
Okay, let's take a quick look at our agenda to get you exam ready. We're going to cover the basics of electric charge, charge versus mass, conservation of charge, quantization of charge, and finally, methods of charging. Let's do this.
Section 1. Basics of electric charge. We're starting right at the absolute foundation of the entire chapter here. So, electric charge. Notice that word, intrinsic. Just like mass, charge is an intrinsic property of matter. What does that actually mean for you? Well, it means it's so fundamental to the universe that we literally can't research what's inside it. We just have to accept that it exists at the very base level of reality.
All right, here are your rapid-fire exam facts, the stuff you need to memorize right now. Charge is universally represented by the symbol Q. Its SI unit, the coulomb. Now remember, it's a scalar quantity, meaning it's got magnitude but absolutely no direction. We've got two types, positive and negative. And of course, the golden rule of electrostatics, right? Like charges repel each other, while unlike charges attract.
Moving on to Section 2, charge versus mass. Let's look at the differences, because professors absolutely love testing these exceptions. The crucial point here is this stark difference between the two. It's a massive concept in physics. A body's mass actually increases when it moves at super high speeds. But its charge? That charge remains completely independent and totally unaffected by how fast it's going. None at all.
And this formula right here brilliantly illustrates the math behind it. It's the formula for relativistic mass. Now, for everyday objects, like cars or baseballs, the velocity v is so incredibly tiny compared to the speed of light c that the mass doesn't noticeably change. But in electrostatics, we're dealing with quantum particles. Electrons can move at 10 to the power of 6 meters per second. At speeds like that, their mass absolutely changes. But again, and I can't stress this enough, their electric charge stays exactly the same.
Section 3. Conservation of charge. Let's jump straight into the first of the two unbreakable laws of electrostatics you're going to need.
The law of conservation of charge simply states this. The total charge of an isolated system is constant. So charge can neither be created nor destroyed. It can only be transferred from one body to another. You know what's really interesting about this? This rule is completely based on experimental evidence. There's no fancy mathematical proof for its origin. It's just experimentally found to be 100% true across the entire universe.
You're going to use this exact algebraic formula to solve isolated system puzzles on the exam. If you've got three bodies in a closed system, you literally just add their charges algebraically. If they bounce around, transfer charge, the final sum has to equal the initial sum. And hey, this perfectly explains nuclear equations too. Like for example, when thorium, which has an atomic number of 90, decays, it releases an alpha particle with a charge of +2. That means the remaining element has to be exactly 88 to perfectly conserve that initial 90. Make sense? Awesome.
Moving right along to Section 4, quantization of charge. This is all about the packaging of charge.
Okay, I need you to burn this number into your memory right now. 1.6 times 10 to the negative 19th coulombs. This is the fundamental charge. It's the exact charge of a single electron, and it is the very smallest charge that can possibly exist independently anywhere in the universe.
Because you obviously can't transfer half an electron, or 2.5 electrons. Any charge on a body must be an exact integer multiple of that fundamental charge. And that concept is perfectly summarized by this essential exam formula right here. Q equals plus or minus n times E. So Q is total charge, E is the electron's charge, and n must always be an integer.
So, let's test your knowledge with a classic numerical exam question to see how this formula actually works in action. If an exam asks if a specific charge of 8 times 10 to the negative 18 coulombs can be given to a body, what do?
Well, you plug it right into the framework. Set up your formula. Q equals n times E. Then, divide the total charge requested by the fundamental charge of one electron. When we crunch the numbers here, that 10 to the negative 19 goes up, becomes positive, and we end up dividing 80 by 1.6, which gives us exactly 50. Since 50 is a perfectly clean integer, the answer is an absolute yes.
we can legally transfer exactly 50 electrons. Now, if this had resulted in, say, 49.8, the answer would be a hard no.
Finally, Section 5, Methods of Charging. We know the rules of charge, but how do we actually force these electrons to transfer in the real world?
Here's your ultimate cheat sheet matrix for the 3 methods of charging. Conduction requires direct contact and works on conductors. Induction involves zero contact and also targets conductors. Friction involves rubbing and is primarily used for insulators. Let's break these down real quick. For conduction, which, remember, requires a direct physical touch, electrons flow from where there are many to where there are few, and here is a massive mathematical shortcut for your exams. Listen up. If the 2 conducting bodies are perfectly identical in shape, size, and material, the total charge splits evenly right down the middle when they touch. So a neutral body and a body with charge Q will both end up with Q over 2. Easy points right there.
Now, induction. This is charging something without ever touching it. It kind of feels like magic, but it's just physics. You have to follow this precise order of operations. First, bring a charged body near a neutral conductor to polarize it, basically pushing the electrons to one side. Second, ground the far end or touch it with another neutral conductor, giving those pushed electrons a path to escape. Finally, cut that escape route and separate the bodies. And boom, you've trapped a permanent opposite charge on the original body without a single touch.
Lastly, we've got friction. When you rub 2 insulators together, you're literally converting kinetic energy into thermal energy. That heat provides the ionization energy needed to violently strip electrons from the outer shell of one material's atoms and transfer them to the other. And hey, here's a tricky question they will definitely ask you on the exam. Does mass change during this process? The answer is yes. Wherever electrons go, a tiny bit of mass goes right along with them. Specifically, 9.1 times 10 to the negative 31 kilograms per electron. So the body that gains electrons gains a tiny bit of mass, and the body that loses them, it loses mass.
You now have an incredibly solid foundation of the rules, behaviors, and creation of electric charges. But to truly master electrostatics and completely dominate this exam, you have to ask yourself, now that we have these charged bodies, how exactly do we calculate the mathematical force pulling them together or pushing them apart? So, are you ready to discover the secrets of Coulomb's law?